machines. So I'll go through the syllabus, like what are the major topics in DC machines, and then we'll start off with the introduction. Okay.
Okay.
The first we have the basics of DC machines. Second, we have the classification. Ramesh, if you didn't understand anytime, you just stop me and ask, okay?
Yes, sir.
So the third topic is the armature reaction, then commutation. Topic we have DC generators, DC generators and types. The fifth topic we have DC motors. Same here also we'll discuss about basics, and the working principle, speed control of DC motors. Last topic we have DC motor types, characteristics. So that's what I have listed here. You see here the same. First, we will start with the basics of DC machine. So, what are DC machines? So, DC machines convert energy from mechanical to electrical and vice versa. So, if it's converted from mechanical to electrical, we call it as a generator, and if it's from electrical to mechanical, we call it as a motor. So, the DC machines can operate in two ways. One is a motoring operation, other one is a generator operation. So, working principle, major principle for the DC machines is the Faraday's laws of electromagnetic induction. Faraday law of electromagnetic induction. What does this law state? So, whenever there is a relative motion between conductor and magnetic field, say let's say this is the north and south pole, the magnetic field direction. So, we have a conductor here. So, whenever this conductor moves within a magnetic field, there will be an EMF induced in this conductor. And the same is given by the expression is equal to BLV sine theta. BIV sine theta. So B is a magnetic field density where I is the current, V is the velocity of the conductor, and theta is the angle with respect to the like how the conductor is moving with respect to the magnetic field. Suppose if the conductor is moving in this direction, field is in this direction, so the angle is 90 degrees. So then the induced EMF is maximum. Instead of suppose instead of moving in the horizontal direction, if the conductor is moving in the vertical direction, then theta is 0 degrees or 180 degrees, right? So in that case, sine theta is 0 and the induced EMF is 0. So that gives us, this expression gives us the magnitude of induced EMF and direction of the induced EMF. That is, suppose I mean, if the conductor is when you place a conductor inside the magnetic field, the current either flows inside the conductor, is cross, or it flows outside the conductor, cross or dot. So this notation is given by the Fleming's right hand rule. I have the consolidated all in the here itself. So Unmesh, are you clear? You have any doubt in this slide?
Yes, sir. Clear, sir.
Go to the next. So now we'll see the direction of the dynamically induced EMF. Earlier I said, right? So whenever the conductor moves parallel, then theta is 180 degrees. So the induced EMF equal to 0. Whenever the conductor moves perpendicular, the induced EMF will be maximum, that is BIV. Now let us consider a single loop generator, which means, let me draw the figure, okay? So this is our magnetic poles, north and south. The field is flowing in this direction. Single loop generator. So only one coil connected to split rings. This split ring is connected to some. So let's say the conductor is moving upward direction. So name the terminals here. So this terminal is going upward. So it is moving perpendicular to this magnetic field. Right? The direction of the current will be, we use the right hand rule. The current goes away, comes here, this direction. So here actually this split ring, this portion of the machine is called as a commutator. 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 So what does this commutator do? This commutator will convert the induced EMF. Generally, the induced EMF in the coil is AC. Okay. Because of this commutator action at the terminals, this resistance will see a DC supply. Okay. Suppose here we have split rings, right? Suppose instead of this split rings, we have slip rings. Slip rings means this is the coil. One terminal is connected to one slip ring, the other one. Here I have the resistor. So if you see this portion of the coil, it always stays in this slip ring, though the coil rotates. But here, if you take this portion of the coil, for 180 degrees it is under this slip ring, and for the remaining 180 degrees it is under this slip ring. Because of this differentiation, commutator action takes place and the AC supply is converted into the DC supply. Okay, so I will show you the slide with a clear picture. So this is the split ring. This is the slip ring. Okay. So when you have slip ring, the induced EMF will be sinusoidal. Okay. Have split ring, this sinusoidal EMF will be converted into the DC EMF as the output or the external load resistor. Is it clear, Unmesh?
Yes, I got it.
Next, we'll see the construction. So I'm going fast. If you find it difficult, let me know, Unmesh, because we have a number of hours for the machines. Okay.
No, sir, I'm understanding.
Okay. Okay. Then fine. So next is the DC machine construction. So generally, there are three main requirements of a DC machine. One is the field, magnetic field. Why we need this field? And this field is produced by means of a field winding. Okay. Second, this field winding creates the flux in the machine. The next we have conductors, because these conductors will cut this magnetic field to get the EMF, and this is called as an armature winding. Okay. And the third one is we have a relative motion. So whenever there is a relative motion between these two, then there will be an induced EMF. Okay. So the purpose of the field winding is to produce flux in the air gap. And okay, and let me draw a figure. Okay. These are called pole shoes. Okay. This is the north pole, south pole. This is our field winding. Pause. Getting the magnet. We have our armature. The armature, we have the armature conductor. These are called brushes. The outer portion, actually, we have some protection made. protection, like case, we have a case around this machine. This case we call it as an yoke. Okay, so yoke generally what it do is it acts as a return path for the flux. Flux flows from this and it then goes back. So this yoke acts as a return path for the flux and it also covers the machine. So it offers the protection. Okay, share you the figure. See? This is what I have drawn. See this brown color is there, right? This is called the yoke. This is the shaft. This is the armature commutator, and we have the slots on this armature, and these are the armature conductors. So this is the field winding. Okay, clear, Ulmesh?
Yes, sir. Clear, sir.
Next we talk about armature winding. What is armature winding? So armature winding is nothing but a conductor. It is connected. It places half of the conductor generally is placed under the north pole, and the remaining half will be placed under the south pole because the EMF induced in this one part of winding should aid the winding, so that the total EMF will be added. Okay, let me pause. These are armature, right? So we have slots here. Here I place the conductor. This is one part of the conductor. So here the conductor is connected. Okay. So here we have north pole, now south pole. So these two EMF induced in these two parts of the conductor will be added. So we'll be getting the resultant EMF across this. This is one coil. Okay. So the distance between these two portions of the coil, okay, coil, right? Coil. So the distance between these two portions of the coil is called coil span. Okay. So if coil span equal to 180 degrees, means the two parts of the winding are placed at the opposite side. Means coil span is 180 degrees. That is called full pitch coil. Okay. The coil span is less than 180 degrees. It is called short coil. Greater than 180 degrees, it is called over pitch coil.
Okay.
So DC machine is trapezoid, not sinusoidal. Generated in DC machine is irrespective of the coil span. Means whatever the coil span is, long or short, so the induced EMF will be same. Because if you see here, it is not sinusoidal. See, if we have a sinusoidal like this, based on the coil position, the magnitude is varying, right?
Hmm.
If you see a flat line or here or here, the magnitude of the flux is same. Now the next, the armature. Generally, the armature has a lot of coils like this, like and so on, n number of coils. So how coil is connected to the another coil? Based on that, the armature winding is classified into two types. One is lap winding, the other one is the wave winding. Show you the figures. See? So here one part of the coil is placed in north pole, the other is in the south pole. So this is the coil. The distance between these two parts of the coil is called as a coil span. Clear, Unmesh?
Sir, this 180 degree is like mechanical 180 degree or
Yes,
electrical?
the mechanical.
Okay.
And it's also electrical because the induced EMFs are opposite to each other. Okay.
Okay. Yes, sir.
Here it is a mechanical, just for representation. If you see here, these two coils, they're at opposite ends. Okay.
Hmm. Hmm. Yes, sir.
To the next slide. So in a lap winding, winding will be connected something like this. The series, the other part will be connected to the series. Show you the figure. This is the lap. Okay. Whereas in case of a wave winding, the winding will be something like this. It will be in the shape of a wave like this. So here we have, these are the commutator segments. Okay. This is the wave winding. The major difference between the lap and wave windings is, in case of a lap winding, the number of parallel paths A equal to number of poles. Actually, this we use in the EMF generation expression. This is required. Hi, Raghuram. Hello, Raghuram. Let me know if I'm not audible. Okay? And here, in case of a wave winding, we have number of parallel paths equal to 2. It's always 2, irrespective of the number of poles. And in case of a lap winding, equalizer rings are used. Equalizer ring is nothing but, so this is our armature. General armature is cylindrical in shape. So at the end of this armature, they will place one more ring, which connects the short circuit of this armature windings. And this is called equalizer ring. Generally, in case of a lap winding, equalizer rings are required uh, for make the winding mechanically more well balanced. Okay. Whereas case of a wave winding, equalizer rings are not required. I'll show you. See here. If you see the lap winding, this is the lap winding. In case of wave winding, it is in the shape of a wave. Mesh, clear?
Sir, where is the parallel path you're talking about?
Yeah, parallel path. Okay, let me draw. You see here, see, this is the commutator. We have different segments, right? So many segments are there. So there is another way to draw this winding. Okay. So we have so many windings on this armature, and these are connected. Okay. So suppose we have two poles. Suppose if you take a wave winding. So generally, wave winding, if the entire winding, if you draw it, it will look something like this. So we have two parallel. This is one parallel path. This is one parallel path. So this is the other way of drawing. Okay. Electrically, if you connect connections, if you see. Okay. If we have two poles. Suppose if we have four poles. For wave winding, number of parallel paths will always be two. If you take the lap winding, we'll be having four poles, right? So here we have one parallel path. So we have four parallel paths. Clear?
Okay, sir.
Program, am I audible? Let me know if you have any doubts. Okay. The next one is the EMF expression. We know that the induced EMF in a DC machine is given by E is equal to phi Zn by 60 into P by A. Okay. So I'll do a quick derivation for you. Okay. So the phi is the flux produced by each pole. Flux produced by each pole. Okay. So let P be the number of poles. So the total flux produced by all poles will be P into phi. Right. Now let N be the speed of the armature in RPM. Okay. Now N is rotations per minute. So for time taken for one revolution will be 60 by N seconds. Okay. You have to take it the other side. Okay. Got it? N revolutions per 60 seconds, right? I want one revolution. So it will be 60 by N seconds. Time taken for one revolution. Now let E. E is the flux, that time taken generally is given by total flux by time taken. So total flux is 5 into P. Time taken is 60 by N. Getting 5 P N by 60, right? That we have how we got the P by A. So that we'll see. So let Z be the total number of conductors, A be the number of parallel paths. Now Z by A gives us the number of conductors connected in series. So so this is the EMF induced in single conductor. So the total number of conductors which are connected in series is Z by A. We have to multiply it with Z by A. So the induced EMF in a DC generator is 5Zn by 60 into P by A.
Okay, sir.
So is the derivation clear? Eligible. If you didn't get any point, you can ask.
Yes, I got it.
So we have one question here. If the number of poles, actually these are two questions. One is lab connected DC generator, other one is wave connected DC generator. So if the number of poles in the lab connected DC generator is doubled, then what will happen to the generated EMF? So will it becomes double or will it becomes half or what is it?
Mm,
I give you a hint. You can solve it. I give you a hint. Okay. Expression which we have derived earlier is 5Zn by 60 P by A. Okay. So let's take first question, that is lap winding. Let us consider the machine is lap winding. Actually, the machine has some P poles. Now, number of poles are doubled. So the P becomes 2P. So what will happen to the EMF? E. Umesh, can you
two.
follow this?
Yes, sir. EMF will double.
How? Okay. Can you?
Hello.
Yes, yes.
Yes, sir. If lap winding, if P is double, then E will also double.
Yeah, but we have parallel paths also, right? Yeah, so
Okay,
what?
yes, sir. Then E will remain constant.
Yeah. Okay. Let me solve that for you. Okay. So, what I suggest you is better to solve before proceeding, okay? Because if we make mistakes, we'll be losing marks, okay? So once
Yes,
you read
yes,
the question carefully and then take some time, solve it, and then put your answer, okay?
yes, yes,
So let's say the initial poles are P1, okay? Now the poles gets doubled. So the new poles is P equal to 2 times P1, okay? Let the initial parallel paths be A1. We know that in a lap winding, number of parallel paths equal to number of poles. Right? A2 will be 2 times
yes, sir.
A1. So if we substitute here, 1 by E2 to equal to P1 by A1, right?
Yes,
What happens?
sir.
Here we have 1 by 2, here we have cancel to E2. So it won't change. So what happens if
Yes,
we
sir.
have a wave winding? Wave winding. So what is the relationship between E1 and V2 if we have a wave winding?
Mm. So, wave winding. So for a wave winding, it's two parallel path.
Just two parallel paths.
Mm,
Will not change.
it will not change. Okay. Sir, but it will be proportional to P.
Yes, P. So P is getting doubled, right?
Yes, sir.
So then what happens? E is proportional to P. So E also gets doubled.
Double, yes, sir.
Here, E1 by E2 equal to A2 by A1. But we know that in a wave winding machine, irrespective of number of poles, the parallel paths are always 2. So these two get cancelled. We know that P2 is
Yes.
equal to 2 times P1. So by is equal to 1 by 2.
Yes, sir.
Clear?
Yes, sir. Clear.
Part. DC machine classification. So DC machines are classified into two types, right? Based on how they operate. Generator. These generators are further classified into two types: separately excited. Other one is the self-excited. These self-excited generators are further classified into two types. One is the generator. Other one is the compound. Compound generators we have two types. One is long mount. Other one is the short. In case of a DC generator, the armature is rotated mechanically. Right? Of a DC motor, armature is excited electrically.
Yes.
At a classification, DC machines classified a motor, generator, separately excited, self-excited, and so on. So I will be explaining each type of generator. Clear?
Yes, sir. Clear.
So we have first we'll start with the separately excited DC generator. So it will be having a field winding. Separately means the field winding is excited separately from that of the armature. So this is connected to load, electrical load or shaft. It is rotated externally by means of a steam turbine or something. Have field winding. This is connected to some external DC field current. The field current goes in armature current. So now the induced, this is the terminal voltage V. The induced EMF is, let's say, or you can call EG. So V can be given as minus. Generally, there are two drops. One is armature resistance drop. This is IARA. Other one is the brush drop. Generally, brush drop will be very negligible. Okay, if they specify the value, you can consider. Otherwise, we can ignore that.
Yes.
We have self-excited generator. In case of self-excited generator, the field winding will be connected to this armature. The, the shaft rotated the terminal IA, armature current, total summation of these both the current. Let's say we call it is armature current IA. IA equal to I load. Now the terminal voltage V equal to minus shunt current or the field current can be given as voltage is same, right? VV.
Yes.
by RS.
Okay.
Is clear? This expression
Yes, sir. Clear. Yes.
one. What generators are classified into two types. One is the short shunt and the other one is the long shunt. That is based on how the field winding is get connected.
Okay.
We have seen shunt field winding and series field winding, right? In case of shunt field winding, we have seen the expression for current, right? ISH or I field equal to V by RSH. The resistance is constant and the terminal voltage is constant. So the field current is constant, because of which the shunt field flux is considered as a constant flux irrespective of the load. Whereas series field flux, whenever we vary the load, what happens is the current flowing through the series field winding will get varied. That's why it is called as a variable flux. The
Okay.
compound is classified as cumulatively compound. This is one more classification. Is short shunt. The other one we have the long winding. Then we have see here the connection point is different.
Yes.
The expression here, the short shunt, the series current ISC equal to the load current. ISC equal to IL. The armature current IA, this current is summation of field current, shunt field current ISH plus series current ISC. Now the terminal voltage we can be given as induced EMF EG minus armature resistance drop IRA minus series field winding resistance drop ISC RSC minus brush drop. In case of a long shunt, the series current is nothing but the armature current. SC equal to IA. The IA is the summation of load current plus terminal voltage is given by V is equal to EG minus IA RA minus ARSC minus brush.
Yes.
Clear, Unmesh?
Yes, sir. Clear, sir.
Yeah. Okay. So see, this is the short shunt and this is the long shunt.
Yes, I got it.
Okay, then we will solve one previous statement. So 8-pole DC generator has a wave winding consisting of 2 coils of 6 turns each. If the flux per pole is 0.06 Weber, the machine is running at 250 RPM. They're asking us to find out the induced armature voltage.
Yes.
So you can use the earlier expression, E is equal to pi Z by 60
Yes, yes.
Try to solve this question.
Okay. 16 will have. Okay, 1 minute. This is 32 volt.
22 coils.
Acha, 32 coils, 6 turns. Okay, into 6.
The difficult part is the calculation of Z.
So 192 volt.
192 volts. Okay, let me do that also. So what they have given us? They have given us 32 coils. That generally is given by 32 coils. And each coil has 6 turns, right? And each turn has 2 conductors.
Yes,
So
yes.
that gives us
Yes.
now the
Oh, okay.
here you have to consider 2 also. Because
Yes, yes.
one has 2 conductors. Fourth is 8. They have given that the machine is wave wound. So wave winded means parallel path we have
2.
5 0.06. So A is equal to 5 Zn by 60 into P by A. So this gives us 0.06 into Z, 32 into 6 into 2 by 60 to P is 8 by 2. 4, 15, 6 into 6 into 2, 4,
384.
50. Got it? Hello.
Yes, sir. Got it.
Got it? Okay.
384 volt.
Yeah.
Yes, sir.
Okay. The next question actually I haven't included here. Okay, I'll write it here. Okay. Have a separately excited DC generator supplies 150 amps to a 145 volt DC grid. So the generator is running at a speed of n equal to 800 RPM. They have given the armature resistance RA of a generator as 0.1 ohm. Now, if the speed of the generator has to be increased, say to N2 equal to 1000 RPM, they want to increase the speed to 1000 RPM. Now, they're asking us to find out the current supplied by DC generator to DC. So a separately excited DC generator is supplying initially 150 amperes to a 145 volt DC grid. At that time, the machine is running at 800 RPM and armature resistance is 0.1 ohm. Now, machine speed is increased to 1000 RPM. So they're asking us to find out current supplied by DC generator to the DC grid in this case. So earlier it is 150 amp. Now what is it? So we have 150
Okay.
amp, 800 RPM. What will be the current at 1000 RPM? So draw the figure for the separately excited DC generator. So, and you can first, and after that you have to find out the induced EMF using the KVL. Then we can use the earlier expression is by 16 to P by A.
Yes, yes. Okay. terminal voltage 145. Sir, resistance is not given. Oh, yes, sir.
Point.
Given. Yes, sir.
That is a series field resistance, or you can take it as armature resistance.
Okay. Yes. 115 to 115. So first generated is a 160 volt, and
Now you find the induced EMF using π/60 into P/8.
1 by 2 and 2 by and 160 and 1 is 800,000.
You carry on. I will also do parallel. Okay.
Okay, yes. E2 is 200. 200 minus. So 550 ampere.
550.
No, 1 second. Oh, 550.
550. Got it?
Yes, got it.
Clear?
Yes, clear.
So not include. Okay. I thought it will take more time. Lot of time, so I can dictate it. So a separately excited DC generator supplies current of 200 amps, 125 volts to a load of constant resistance. When driven at speed of 1200 RPM. Now they're asking us to find the current delivered when speed is 2000 RPM. So they have specified that excitation unaltered. It is not changed. The field current is same.
Okay.
The armature resistance is 0.04 ohms. They have given us the brush drop as 2 volts. So a separately excited DC generator is initially supplying current of 200 amps at 125 volts, and the machine is running at 1200 amps. Now
Yes.
they're asking us to find out current, and the speed is reduced to 1000 RPM. They have given us the armature resistance and the brush drop.
Yes.
Right.
125.
I'll be back in a minute. Okay, try to solve this.
Okay.
Are you done, Unmesh?
No, sir.
Okay, okay, you carry on. I will also do that.
Okay. I'm getting in minus.
Minus current.
Not current. This is a current.
Current, you will get a quadratic equation.
Yes, sir.
Here, let me explain. See. So this is our separately excited DC generator. 2 volt is a brush drop. This is the armature resistance 0.04 and 200 amps is flowing. and the terminal voltage is 125 volts. So that load resistance can be
Yes, sir.
given as 125 by 200. So now if I calculate EG of EG1 equal to 125 plus IARA 200.4
Yes, sir.
plus that is 135 volts. We know that the induced EMF is given by pi z by 60 into P by A into N. We know N. So the remaining thing we can call it as a constant. So K
Yes,
into
sir.
100 equal to 135. K is 135 by 1200. I can write E2 equal to K into 1000 RPM. This is N2. This is a constant, right? So K into 1000 RPM equal to brush drop 200 plus 0.04 into the new current. When the machine is running at 1000 RPM, we have to find out the new current. So that is I into load resistance, that is 125 by 200, that is 5 by 8 into the new current I. So this is a quadratic equation. So to solve this quadratic equation, getting around 66 amps.
Okay.
Yeah, take your time. You just go through it once again.
Sir, I took that 125 in second case also, terminal voltage.
Okay, okay. No, because the terminal voltage will change, right? Because the machine speed has increased. Now
Yes,
the
sir.
speed decreased in this case.
Decreases.
So it
Yes, sir.
increased when compared to the earlier case. So the terminal voltage will be changed. It won't be same.
Okay, okay. Yes, sir. Okay, then yes, sir. Got it. Yes, sir. Got it, sir. So not able to hear you.
Yeah, no, no. I was looking if there are any
Okay. Yes, sir.
all remind questions. Actually, there are two rules. One is the Fleming's left hand rule. Other one is the Fleming's right hand rule. The Fleming's left hand rule gives us the generally it is used for motors. So
Okay.
whenever a current carrying conductor is placed in a magnetic field, the motion, the direction of that conductor is given by the Fleming's left hand rule. As the Fleming's right hand rule is used for generators. So whenever the conductor is moving in a magnetic field, so it gives us the direction of the current, either dot or cross. Okay,
Yes.
I will show you a figure. First one is Fleming's left hand rule. So whenever
Yes.
the conductor is moving in this direction in a magnetic field, the flow of current is given by Fleming's left hand rule. Similarly, Fleming's right hand rule, whenever the current is flowing in this direction through a conductor, it will experience a force in this direction.
Yes, sir.
Armature reaction. What is this armature reaction? Generally, we have field windings, right? So this is our field, north pole, south pole. This is our armature. It has some magnetic field direction, poles. This is the shaft, and the armature is rotating. So whenever this
Yes.
conductor rotates in this magnetic field, there will be an EMF induced in this conductor. Since the conductors are connected, there will be a current flowing through this conductor. Right? So because of this current flow through this conductor, you know that Ampere's right hand rule, right? Crookes,
Yes, sir.
remember the Crookes rule? The
Yes,
law
sir.
produces direction of the current, then the four fingers gives us the flux direction.
Yes, sir.
So whenever the current flows through the conductor, it produces the flux. So that flux is called as an armature flux. So these all conductors are producing the flux. The flow of armature current. This flux is called as an armature flux. So what happens is this armature flux may interact with our main field flux. So this interaction is called as an armature reaction. So the effect of armature flux on the main flux in the air gap is called as an armature reaction. So the armature generally depends upon the load on DC machine, because whenever the load on the DC generator is varies, the armature current varies. So the armature flux varies. So the effect of armature flux on the main field flux will vary. So as load increases, the effect of armature reaction increases. Load decreases, the effect of armature reaction decreases. So
Yes, sir.
that the main field flux is a trapezoidal in shape, not a sinusoidal. So it is a trapezoidal shape. So the main field is
Sir, one doubt, sir.
yes.
Sir, load means some resistor will be connected.
Yeah, and yes, this is the poles, right? So here we have our terminals. Here we'll be connecting some load. For a generator, generally, any load, say we connect a bulb or connected
Yes.
a rheostat I have connected, anything.
Sir, if the load means resistor will increase,
Uh,
then the value of current will decrease.
yeah, the current will change. So whenever the current changes, what happens is the flux will change, right?
Yes, sir.
So the armature flux will change. So the position, suppose let's say the current is 10 amps, okay? Phi A is the armature flux. Let's call it 1 Weber. That's Now what happens? These two are generally proportional. Now the current reduced 5 amps. Flux, what happens to armature flux? It becomes zero point 0.5 Weber. It will reduce, right? So
Yes,
say
sir.
our
Yes.
main field flux is always say 2 Weber, for example.
Okay.
Two are suppose these two are opposing. The opposition is less, right?
Yes, sir.
Now here it is further decrease. Zero point 0.5 is opposing to plus compared to one opposing 2. But
Yes. Yes, sir.
so the main field flux in the air gap sinusoidal. The main field flux is maximum along the magnetic neutral. See, this axis is called the magnetic neutral. Main field flux is always be maximum along this magnetic neutral axis. Now, see, this is the main field flux distribution, right? Similarly, if you draw the armature flux distribution, phi A, generally it looks triangular. Okay.
Okay.
Actually, we can see why it is triangular, but I think it's not needed actually. This is it will take time. It's not needed for this.
It's okay. Yes, sir. Yes, sir.
So,
Okay. So for armature, it is triangular,
uh,
and main flux is like trapezoidal.
now we have to see how, when these two gets interact, how the resultant flux will look.
Okay. Yes, sir.
This is north. I'm just opening the. This is the north pole. Here we have south pole. Okay. Exactly. So we know that along the pole, the main field will be maximum. It again decreases and maximum along the south pole. Max along the south pole. So it is a trapezoidal.
Okay. Yes, sir.
Now the armature flux. This is our magnetic neutral axis when it crosses zero. So the axis where the main field flux crosses zero is a magnetic neutral axis.
Mm. Yes.
Now the armature flux is triangular in shape. Here and then it goes. So this is our phi. This is our main field flux. Let's say phi. Now if you see, if I draw the resultant, here it is see, here the armature flux is more negative, right? Here it is
Yes, sir.
less positive. So So the resultant will look something like this. After that, this is constant, this is increasing. So it gets increased till here. This is decreasing, this is also decreasing. So the resultant also decreases. So this is, we call it as resultant flux. Okay.
Okay.
So if you see here in this region, this is positive, this is negative. So the net flux will decrease. Okay.
Yes,
Here
sir.
this is positive and this is also positive. Here the net flux will increase.
Positive. Yes, sir.
So at some point we have add additive effect. At some
Okay.
point we have, sorry, this is subtractive effect. And here we have additive, right?
Yes, sir.
So the subtract effect generally we call it as demagnetization. Additive is magnetization. So the R
Yes.
flux can be divided into two components. One is the demagnetizing component, other one is a cross magnetizing component. Demagnetizing component is because of which net flux will decrease. Cross magnetizing effect, because of cross magnetizing effect, what will happen is the flux quantity won't change, the amount won't change. What happens is the direction will change. That resultant flux axis will change. Okay, because of which what will happen is it will results in a sparking at the commutator. Actually. Suppose so, this is our commutator, right? So here we have pole. These are the poles. These are commutator windings. So if you take main field flux, this is the magnetic neutral axis, and the flux is maximum here in this region. Whereas at poles, there is no very less flux, because of which the conductors in this region there is no EMF induced. Okay, so there won't be any sparking. Okay, actually the sparking is due to delayed compression that we'll see later on. Okay, for now you remember that armature flux is divided into two components. One is the cross magnetizing, other one is the demagnetizing component. So the
Yes.
demagnetizing component acts in opposite direction to net field flux. So here this one subtractive effect, because of which the net flux will decrease. The cross magnetizing effect will increase the flux at the trailing tip and decrease the flux at the leading tips. Okay, trailing and leading are these tips. This one is a trailing tip and this is the leading tip of the machine. What happened? Because of which what happened earlier? This is the MNA. So what happens is because of the armature reaction, the MNA gets shifted, so it becomes close to this pole. So generally, because of which sparking takes.
Okay. Yes.
So you're clear?
Yes, sir. Clear.
I'll show you a better picture in this slide.
So this trailing pole I didn't get.
Yeah, I will explain. See, this is the old MNA. That means without the armature reaction. What happens is MNA is where the flux crosses zero. Now, because of the armature reaction, this is the resultant flux. And the resultant flux is crossing zero at here. Because of which the MNA gets shifted. Okay.
Yes.
So generally poles are located uh, at the old MNA point. The old MNA. Okay, in this figure it is not clear. Okay, you want the leading and trailing tips, right? See. Actually, this is our direction. Actually, these tips are called these are tips, and then are called tips. The leading and the trailing means the armature enters that first. That tip comes first. This is the leading. If it comes later, then it is called the trailing. Okay, based on the
Okay.
direction of the armature.
Okay.
Generally, it's not important. Whatever you remember that because of the cross magnetizing effect, the magnetic neutral axis position will change, because of which it results in a spark or the commutation surface.
Yes, sir.
Now we have seen that the armature MMF can be divided into two types. One is a demagnetizing, other one is a cross magnetizing. So generally we have questions here. They will ask us to find out the demagnetizing ampere turns per pole and the cross magnetizing ampere turns per pole. So it's a derivation, it will take time. It is not needed. Derivation is not needed for Hall exam. So
Yes, sir.
basically, we will go through the formula once.
Okay.
So the demagnetizing ampere turns per pole is given by ATD per pole equal to ZI theta m by 360 degrees. Similarly, the cross magnetizing ampere turns per pole ZI 1 by 2p minus theta m by 360 degrees. So Z is a total number of armature conductors, T is a number of poles, I is a current to each armature conductor. So I is given by armature conductor current, total armature current by A, number of parallel paths. This uses the armature current to each armature conductor. And MNA, this theta M is the shifting angle. So earlier we have seen, right? Without armature reaction, this is the MNA. But when the armature reaction happens, the MNA gets shifted. So there is a shift in angle. This shift in angle in mechanical degrees is given by theta.
Yes, sir. Okay.
Generally, demagnetizing effect can be nullified by increasing the field current. One, by increasing the field current. That is one way, or by increasing the number of field, either increase the field current value or increase the number of turns.
Yes, sir.
Cross magnetizing effect of armature reaction can be compensated by using compensating windings. So these compensating windings are placed within the pole itself. See, here we have pole, right? This is our pole. This is our armature. So here they will have some drill holes, and in this they will place conductors. These conductors are called as a compensating winding. Compensating winding. So, and these conductors are connected in series with the armature. So the compensating winding will increase the flux. Earlier we have seen, right? So what happens is now the angle is shifting like this. However, this what will do, because of the compensating winding, it will increase. Because of cross magnetizing effect, what will happen is at one end of the tip, flux will decrease, and other end will increase, because of which the MNA is shifted. So this cross magnetizing, cross compensating winding, what it will do is it will increase the flux in the region where the flux has decreased earlier. So because of which it will bring the MNA back.
Okay. Yes, sir.
Compensating winding increases the flux value at the leading and decreases the flux value at the trailing. So hence the air gap flux value is brought back to the trapezoidal. Okay,
Okay. Yes, sir.
slide on. So this is the ATD per pole, this is ATC per pole.
Sir, means these ampere terms are required to compensate.
Yeah, this much amount of ampere turns is required to compensate.
Okay. Okay.
Clear?
Yes, sir. Clear, sir.
Okay. Earlier we have seen, right, when this armature reaction, we are having sparking on the computation surface. So why that happens? This is a commutator. We have a lot of segments. We have three segments here. A, B, C. This is the brush. Brush position is fixed. However, the commutator will move. So let's say
Yes.
initially this winding is carrying 20 amps. This is also carrying 20 amps. So total 40 amps it is flowing through the brush.
Okay.
Now what happens? The commutator is moving in this direction, but the brush is fixed. Let's say after some time what happens is The commutator segments are this is A and this is B. Okay. Now here, now 20 is flowing, 20 is flowing. So the brush is in this direction, 20 it is coming, 20 it is coming. So 40 is fine.
Yes.
So still, if the commutator moves further, now 30 is coming, 10 is coming. Got it right? Why it is changing? Why now it is increased? Why this got decreased? Because the conductor is moving. It is moving. The magnetic field is increasing. This side the magnetic field is increasing. This side the magnetic field is increasing because we have a trapezoidal shape, right?
Yes, sir.
So at this edge, if you see this edge, here the flux is high, again decreasing, and then
Decreasing. Yes,
got it? That's why the current is
yes,
moving. Now
yes,
what happens is generally because of this armature reaction, earlier there is no flux in this region, right? This region there is no flux.
yes, sir.
The MNA gets shifted here. So what happens is because of which there will be an EMF induced in this conductor. And this EMF, what it will do is Lenz's law. According to Lenz's law, we know that effect opposes the charge, right?
Yes,
So this induced EMF will oppose the. This is nothing but an inductor, right? So it will oppose the sudden changes in current. The
yes,
what happens is actually if it further moves, it should be 35 amps and this should be 5 amps. Again, we'll be getting 40 amps. But what happens is suppose commutator segment. One segment is here. Now the brush is connected here. See, this 5 amps is going in B segment, but B segment is not connected to it, right?
yes, sir.
So this 5 amperes has to be taken out. So it will flow
Hmm.
through this air gap in the form of a
Okay, yes,
so earlier it is 40 amps. Now the current will become minus 40 or you can say 20 amps. Say I will take one part. So in this point 20 is
20.
going
Yes, yes,
become after that it is becoming 5 and then it becomes 0. So it
0.
again minus 20. So this time is called as a commutation time.
Okay,
Commutation time. That ideally if it gets 0, when I mean if the current becomes plus 20 to minus 20 with this time, then there won't be any spark. But what happens is because of the shift in MNA, there will be EMF in these coils because of at poles. So instead of the current becoming plus 20 to minus 20 between PC, it will take more time. See, it is taking more. So
okay,
difference in time because of which this effect has to be taken out. So that current flows through the air gap, resulting in a spark.
yes, sir.
I'll show you the figure. The better way. See, this is the commutation time. 20, it has to be minus 20, but it is not going till minus 20. See, it is going till only 5.
Yes, sir.
15 is 15
15.
given here. It has to go to minus 20, but that 5 ampere is left. So that 5 ampere will be taken through the air gap in the form
Yes,
of
sir.
a okay.
Yes, sir. Got it.
So why this delay? Delay is happening. This is called delayed computation. Why this delay is happening? The delay is due to the induced EMF. That EMF we call it as a reactance EMF. This reactance EMF is an EMF produced in the coil under computation is called reactance EMF.
Okay, yes, sir.
That slide also. The reactance EMF.
Yep.
So if you reduce the magnitude of the reactance EMF, generally the sparking decreases. So what are the methods to improve the commutation? There are two methods. One is a resistance commutation, and by providing endpoints or COM pole. Resistance commutation is generally we use the brushes are replaced with the carbon brushes. So a low resistance copper brushes are replaced with high resistance carbon brushes. That is resistance commutation. The other one is by improving the interpoles or compoles. So these are the additional poles. The main field poles, and they will be adding two more poles called as an interpoles. They are also called as a compoles. So they will inject an EMF in a direction opposite to that of the reactance EMF. So both will get cancelled out, and thereby the delayed commutation can be avoided.
Okay. Yes, sir. Yes, sir.
The resistance commutation, what happens is generally if you see an RL circuit, in RL circuit, uh, we see networks. By varying the value of RL, uh, uh, I can say the damping will be improved. The response becomes fast. Have you noticed that if you take an RL circuit, maybe in networks, you have seen that we'll derive an expression, right, for the current.
Yes, sir.
Next we'll
So in
see.
control, sir, there is damping.
I didn't get you. Hello.
Hello.
Yes.
Yes, sir. So in control, there is a damping control system.
Yeah, control system we have done. That is okay. I'm not talking about the control system. In general, I'm saying, suppose if we have an R at least say 100 millihenry, and I have the resistance, and I'm varying the resistance from 1 to 100 ohm.
Yes, sir.
You take a DC source connected to this RL circuit, and you can derive the expression for current, right? So if you plot this current with various values of resistance, you can see that the response of the current becomes faster.
Okay.
That's what I'm saying. So when we have a carbon brushes, generally they have more resistance. So earlier we have only inductance and less resistance. When we are replacing these copper brushes with carbon brushes, the resistance is increasing. So R is added to the RL side. Thereby response becomes faster. Okay.
Okay. Yes.
Next we'll see some good questions. Okay. These are not numericals. Okay. First question is a GATE 2001 mark. The compensating winding in a DC machine. So what does the compensating winding do in a DC machine? Is located in the armature slots for a compensation of armature reaction, located on commutator poles for improving commutation, or located on pole shoes for avoiding the flashover at the commutator surface, or is it located on the pole shoes to avoid the sparking at the brushes?
So this is avoid sparking at the brushes.
I didn't get you off.
Sir, option D.
To avoid sparking. Generally, sparking we talk with respect to the commutator. See, sparking, the other way of saying is the flashover. Flashover is nothing but what happens. Earlier, we have seen that 5 amp current is left out, right? So that 5 amp current is
Yes, sir.
through the area. So it's nothing but a flashover. Okay?
Yes, sir.
So the computation winding is used to nullify the cross magnetizing effect of armature reaction.
Okay.
So option is C, located on the pole shoot for avoiding flash off at the commutator surface.
Okay.
The next question. Gate 2006 one more question. Which of the following statements are true in a DC machine? Compensating winding is used for neutralizing armature reaction. Actually, these are the four combinations of compensating winding and the interpole winding. So go
Okay.
through and let me know the answer.
So this option is not means clearly
Is it
visible.
okay? Okay, let me. Okay.
Oh, now it's okay. Yes. Interpol stop producing armature valid coil. Sir, B.
Yeah, correct. B. Compensating winding is used for neutralizing armaturation, while interpoles are used for commutation. The gate 97, 5 marks. Try to solve this.
Pole pitch.
A 200 volts, 10 kilowatt app connected DC generator has 10 poles and 500 conductors on its armature. The pole phase covers 80% of the pole pitch. The pole phase conductors required to fully compensate for the armature reaction will be. Yes.
Okay, so that formula for what?
Yeah. Use the formula.
Sir, I forgot the formula.
Give me a minute. So 80 compensating, right? So ATC per pole.
Okay.
This one.
Okay.
ZI into 1 by 2p minus theta m by
360. Okay, sir.
but here actually we can't use the formula because he hasn't given the theta m for us.
Oh, yes, sir.
So the compensating ampere turns AC per pole can be given as total ampere turns per pole to pole arc by. Actually, he has given this ratio pole arc by pole pitch. He has specified 80 percentage, right? The pole phase covers 80 percentage of the pole pitch. So that is 0.8. Ampere turns, total ampere turns per pole is Z into armature current IA by 2 into parallel paths into P. Z is 500, 2 parallel paths equal to poles equal to 8, 0.8, 3.125.
Okay. So this is the another formula.
Yeah, this is another formula.
Okay.
To solve this one, this I think we can use our formula.
Mm, Demounted.
Four pole tap connected. Z equal to diagonally shifted by 10 degrees.
10 degree.
Per pole equal to
Z I by theta by 360.
I is nothing but 80. 80 current they have given 80 amps at M1. 80 amps at M1.
Okay, armature current is
80 by
by 4
4.
to 10 by 360.
This gives 4. 80 C per pole. Zi into 1 by 2 pi theta angle. Pi, that is 2. 555.5. Is it clear, Unmesh?
Yes, sir, clear.
So, okay, yeah, that's all for today. We'll continue in the next class. And you're a passed out student?
No, sir, final.
Final year. Okay.
Yes.
You're from Bangalore?
No, sir. I'm from this, Odisha.
Okay, okay, okay. Okay then. Okay, we'll see you in the next class.
Okay. Okay. Thank you, sir.